Okay, let's get started, please. Okay, so I said that I'd give you some explanation this time about why if you have some matrix, the dimensions of the row space and the dimension of the column space are exactly the same. Right? So recall when we were examining the rank. Right? The rank was the dimension. We said that was the dimension of the column space. Right? The rank was defined as the dimension of the column space. Right? The column space, which we now recognize as the same thing as the range of A. The dimension of the column space. And what we said was that, in fact, the dimension of the row space also was the same thing as the dimension of the column space, and so we didn't need another name for it. Right? We called that thing, both of those things are called the rank. You remember how we did it? We used the we reduced to row echelon form, and then blah 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 blah. We did something there. Okay. So. That was nice, but now we can see a bit more clearly why this happens. So why does this happen? Right. Why does it happen that the dimension of RAT equals the dimension of R? And here's why. T sub A as a map from the range of A transpose to the range of A is actually an isomorphism. Is actually an isomorphism. So these ranges are in fact the range of A and the range of A transpose are in fact isomorphic to each other via left multiplication by A. And being isomorphic, that tells us that they'll have the same dimension. So you could you might on seeing this statement say, who cares? Why is the fact that this and this are isomorphic to each other not impressive at all? Why is that not particularly exciting? You have this subspace, you have this subspace, and we know that their dimensions are the same from what we did before, right? Why are they isomorphic? Why are they automatically isomorphic? Well, if say this thing is n-dimensional, and this thing is n-dimensional, right? If this thing is n-dimensional, you know that it's isomorphic to Rn, right? Any n-dimensional vector space is going to be isomorphic to Rn. You just take a basis of it and then use the coordinate vector map from, right? So if you have any vector space, right? So if V is any vector space, say n-dimensional, you just take some basis of it, right? And that will give you a map from V to Rn, namely the map that goes from V to the coordinate vector with respect to that basis, right? And that map is an isomorphism, right? So V is isomorphic to Rn, and so each of these guys would be isomorphic to the same Euclidean space, and so they'd be isomorphic to each other. Okay, so that's maybe not exciting. It's not exciting to say that these things are isomorphic to each other. But what's cool is that it's this, right? That actually left multiplication by A is the isomorphism. Gives the isomorphism. So it's not just some arbitrary map. It's if you left multiply this range by A, it gives you an isomorphism to the range of A. So that's what's cool about it. Okay. So let me Let me start the reasoning over here. So let's see. So let's say that A is an n by n matrix, right? T sub A goes from Rn to Rn, right? It takes n by 1 guys and gives you back m by 1 guys. Now, the range of A transpose is a subset, a subspace of Rn. The range of A transpose, right? A transpose is an n by m guy, right? Right, that's right. Right. A transpose is an n by m guy, right? It goes from Rm into Rn, right? So the range of A transpose is in Rn. And so, what does that tell us? We have a subspace of Rn, and so we can break Rn into a direct sum. Right? We have a subspace. We can break it into the direct sum of this subspace and its orthogonal complement. Yeah, Mia.
So, all subspaces can be broken into a direct sum.
That's right. Remember
Okay.
last time we said
Yeah.
that if S is any subspace of Rn, then in fact Rn can be realized as S direct sum S per. Right? We had this theorem last time. That any subspace, if you have any subspace of Rn, then Rn can be realized as a direct sum of this subspace and its orthogonal complement. Right? And so we're using that here. We have a subspace of Rn, and so Rn can be broken up like this. Yeah, Teresa.
Just to review, what does direct sum mean?
So, right, direct sum means that everybody can be realized as a sum of somebody in here plus somebody in here,
Okay.
right? And that expression is unique,
Okay.
right?
The
That-
circle means it's unique. What does this mean?
Yeah. So recall.
Sorry.
Yeah, that's okay. It's sort of an odd concept. Right. So S being. W being U direct sum B, right? Where U and B. So you have W some vector space, W a vector space, U and B subspaces of W. Okay. W being a direct sum means that every W in W can be uniquely expressed as U plus B, where U is in U and B is in B.
Okay.
The way you want to think about this is just think like in R3, you can write R3 as R plus R2, where you have something like this. Let's say that this is your R, and then this is your R2 down here. Right? Everybody in R3 can be expressed as something in this R, right, as some 0, 0, z plus something x, y, 0.
Yeah.
Right, x, y, everything can be expressed like this, and this is done in a unique way. There's no other way to do this. Okay, so R3 is a direct sum of these two things. Okay, yeah, Mia.
So, a direct sum isn't like an operation, really. Like you can't, like when you see S direct sum S, orthogonal, or it's not like you'd have to find the two.
Are you saying, like, suppose you have two
It's not
arbitrary...
like matrix multiplication,
No,
right? Okay.
no. It's sort of the opposite. Rather, you take your space and you break it into a direct sum.
Okay.
Rather than say, I've got one space and I'm going to direct sum it with some other space.
Yeah,
you might not be able to do that,
Okay.
right? Because if they're the same space, it makes, suppose you take this z-axis and the z-axis. It makes no sense to say, I'm going to take the z-axis and direct sum it with the z-axis itself, because they have to be spaces for which this holds.
Okay.
Yeah. So it's more like the opposite thing. You have a space, and then you break it up into a direct sum of subspaces.
Okay.
Yeah. Okay. One of your exercises, I think, is to show that W being a direct sum is the same thing as saying that W is U plus V, and U intersect V is zero, the zero vector. Okay, where U plus V is just the collection of all sums U plus little v. Okay, so that is being a direct sum actually turns out to be, I'm pretty sure this is one of your homework problems, turns out to be the same thing as saying that everybody in W can be realized as a sum of these guys, and the intersection of these guys is zero. The intersection of these spaces is zero. So, for example, right, if here's my space U, right, and here's my subspace V, and I notice that everything in R3 can be realized as somebody in U plus somebody in V, and I also notice that their intersection is only the origin. Then I'd say, okay, then these guys are make a direct sum of the whole space. Okay, but if I had, like, V was, say, this plane, right, and U was this plane, then even though the first is true, right, the whole, R3 is in this case R3 is U plus V, but the intersection is not zero, so R is not a direct sum of these guys. Okay. R is not a direct sum of these guys. Yeah. Everyone sort of getting a sense of what direct sum is? It's kind of an odd notion. Okay. But just keep in mind, keep in mind some picture in your head. Right? You've got these things. You've got these two spaces whose sum is the whole space, and their intersection is zero. Okay. So let's see if we can get back to the idea here. This makes me feel like I should assign homework every day rather than just once a week, because then you guys would be forced to know what direct sum is by today. Okay, so remember what we're trying to do? We're trying to show that RAT is isomorphic to RA, right? That's what we're trying to show. Well, let's take the matrix A. Let's take the linear transformation you get by left multiplication. Okay. And we notice that RAT, right? The range of AT is a subset of Rn, and so Rn can be expressed as a direct sum of RAT plus the orthogonal complement of RT. Because we had this theorem from before that if you have any subspace, then subspace of Rn, then Rn can be expressed as a direct sum of that subspace plus its orthogonal complement. So that's where we are. Rn can be written like this. We use the fundamental subspaces theorem here, right? Right. The orthogonal complement of the range of the transpose is the same thing as the null space of the original space. so what we have now is that any x in Rn, any x in Rn can be written as u plus v, where this u is in the range of A transpose, and the v is in the null space of A, and this expression is unique. Okay. Notice then that AX is going to be AU plus AV. Okay. But V is in the null space of A, so this is 0, and so this is AU. Okay. Everyone with me so far? Okay. So now observe that T sub A, right? T sub A goes from Rn into Rn, right? But I can replace this Rm by the range of A, right? Because we're left multiplying by A, right? Really, the range is the range of this thing is the range of A, right? Tautologically, right? We're left multiplying by A, so that the range is the range. And I'm going to replace this Rn by range of A T, direct sum range, null space of A. Okay, right. So wait, this thing is Rn. This thing is Rn, and this thing lies inside of Rn. Okay, so first thing observe is that this thing maps RAT onto the range of A. Right, is that clear? I think that's clear. Right, TA acts on Rn, and then the collection of all outputs is exactly the range of A, right? So TA acts on this thing, and then everything that comes out of it is the range of A. But TA is acting on this thing here, right? This part just goes to 0. This part just goes to 0. So it's this thing that gets mapped onto RA, right? It's TA acting on this that generates the range of A, right? Because the null space just goes to 0. Yeah.
So the left multiplication of A and A transpose equals the column space of A, right? No, that's
It says that if you take the column space of the transpose, and hit that with A, then you get the column space of the original.
Okay.
Yeah, exactly. Yeah, the column space, right? If you take the column space of the transpose and map that thing through A, then you get that. You get the range of A. Second thing, any other questions? Second thing, T sub A is actually 1-to-1 on RAT. Since why? If U1 and U2 are in RAT, and AU1 equals AU2, then that shows that AU1 minus U2 is 0. Right. But that would say that U1 minus U2 lies in RAT, and it also lies in null space of A. Right? But the intersection of those guys, right? Remember, the null space of A is the same thing as RAT perm, right? The intersection of this with that is 0. And so that tells you that U1 must equal U2. So if the outputs are equal, then the inputs are equal. And so T is a one-to-one map there. Just 1 second, Mia. And so what does that give you? Right? T maps this onto that, and T is one-to-one there. Right? So altogether, 1 and 2 tell you that T sub A is an isomorphism. Right, from RAT onto RA. Okay, Mia, what's the question?
Why does U1 minus U2 exist in our A transpose?
Well, U1 and U2 individually are members of this subspace.
Oh.
And so, being members of subspace, their difference is also in the subspace.
Okay.
Right. You've got 2 guys in the subspace, then any linear combination of those 2 guys will still be in the subspace. In particular, this one. Questions? That's the end. So, so that shows you that right. That shows you that T sub A considered this thing actually gives an isomorphism from here to here. Right, that's the conclusion. So these things, so even if we didn't know already that they had the same dimension, at this point now we would know, right? These things are subspaces, and in fact they're isomorphic to each other, so they're guaranteed to have the same dimension. And you notice we didn't use the fact that they have the same dimension to notice this, to get the isomorphism. I feel like somebody should ask a question. Henry, ask me a question.
So back there.
Yeah, great, thank you.
So we just have how do we flip from like A and then U1 minus U2 is equal to 0?
Yeah.
And then you have U1 minus U2 is within the intersection of RA transpose and the null space.
Yeah. Yeah, so, right, so what are we trying to do here? We're trying to show that this thing is a one-to-one map. What does one-to-one mean? One-to-one means that if the outputs are the same, then the inputs must have been the same. Okay, that is, right, if the function gives you the same outputs for these 2 things, then you know that the inputs must have been identical to each other. Right? That's what one-to-one means. So suppose the outputs are the same. So right, suppose you have 2 guys and the outputs are the same. Okay. And we're going to show that, lo and behold, the inputs must have been the same. In other words, this guy is one-to-one. Okay? So let's suppose the outputs are the same. If we look at the if we take the difference, we see that a times the difference is 0. Right? What does that tell us? That tells us that this thing is in the null space. Right? This thing is in the null space, right? Because it got killed by A. Right? So this thing is in the null space. But we also know that this thing lies in our RAT, right? Because these guys are in RAT, and so their difference lies in RAT, right? RAT is a subspace, right? So the difference lies in RAT, and the difference also lies in the null space. But by the fundamental subspaces theorem, the null space is the orthogonal complement of the range of the transpose of A, right? So this thing lies in the intersection of this subspace and its orthogonal complement. But the intersection of a subspace and an orthogonal complement is 0, right? So that tells you that this minus this is 0. In other words, U1 equals U2.
All right. Thank you.
So yeah, and then that plus the previous fact gives you that that we have an isomorphism. Okay, I'm going to erase. Okay. Why are you guys laughing? Because of Henry?
I give myself a high five.
I see.
Sometimes you gotta show yourself some love.
Okay. My kids do that to each other, actually. Like, my daughter will say, "Good job, Taki, high five," and then like they'll high five each other. Yeah, like if you did something successful.
Sure, got high five.
But you see that sort of like confirms to me that they're really Americans. Like I don't think I ever did such a thing, with my siblings, because although I was born in America, my parents are from Taiwan, and so I sort of feel like still our house was part of Taiwan. But yeah. Okay, something great is the next section, method of least squares. Okay, so this is a really nice application of the ideas of the previous section. So here's the motivation. Suppose we have an overdetermined linear system. Okay. So it's like this. AX equals B, but an A is an m by n matrix, and m is bigger than n. So you've got more equations than unknowns. You have too many equations. Right? You have too many equations. It's over specified. Okay. So in general, such a system is unsolvable. Right? It's like saying, I'd like to have a parabola that passes through these 4 points, right? Mm-hmm. 3 points specify a parabola, right? Or it's like saying, I'd like to have a line that passes through these 3 points. Right? 2 points determine a line. We've over-determined. We've got too much information. Right? You can't get a line that passes through these things. You can't get a parabola that passes through these 4 points. Well, maybe unless you're very lucky. Okay. So instead of solving the system, instead of attempting to solve the system, we solve a different problem. Solve a different problem, which is find x in Rn so that ax hat minus b is minimal, has a minimal norm. Okay. Right. So you'd really like to get ax such that you'd like to get an x such that ax equals b, but it's impossible. There is no such x. So instead, you say, well, I'm going to look at all possible, I'm going to look over all possible x's, and then choose the one for which ax minus b is smallest. Okay, right? And that solution is called the least, so-called least, or a least squares solution. Okay, so the problem is, does such a vector exist? That should be your first question. So let's rephrase the problem. Let's rephrase the problem just a little bit. Okay, so we want to minimize ax plus b, ax minus b, the norm of that, right? So that's going to be the same thing as saying that we want to find p equals ax in the range of a, such that p minus b is minimal. So we just call this thing p. Okay, that's all we did. Call this thing p, and we want let p range over the range of a, right? And we're looking for the p. We want the p in the range of a, such that this is minimal. That's the same thing, right? Right. The first thing we have is we want x hat in Rn so that this is minimal. Second thing is we're saying we want p in the range of a such that p minus b is minimal. Right? You know, this thing is in the range of a. Right? So what are we doing? We're looking over all. We're trying to find, you know, the p in the range of a such that this is minimal. It's not exactly the same problem, but it's pretty close. Okay, so that gives us a picture. Wait, Mia, you had a question?
Yeah, what, by minimal, do you just mean like the
Smallest.
Smallest,
Yeah,
okay.
yeah, smallest. That gives us a picture. Right. There's some vector b, and there's the subspace R of a. Right. We want p in R of a so that p P minus B is minimal. Right, so we want, right, we're letting P range over, you know, over the whole thing, and we like the one for which the difference is smallest. Okay. And this turns out to be a problem of that can be resolved using orthogonality. Okay. So what will happen, what we'll see is that it will be the one, the P that we're looking for is the one for which the difference is orthogonal to the subspace. Okay, so here is the useful theorem for us. So let S be a subspace of Rn, and let V be in Rn. Then, when there exists a unique vector P in S such that B minus P is minimized. In other words, B minus Y is going to be bigger than B minus P for all Y in S. So here's really what we mean by minimized. Right, that if you take any other vector, then you're going to get a bigger value.
Okay.
By 2, P will turn out to be that closest vector if and only if B minus P is in S perp. So it turns out that it will be there's only going to be one vector that does this, and it's going to be the vector for which, if you take the difference of these guys, then the difference is orthogonal to the space. The proof relies on the direct sum decomposition. Say, well, S is a subspace of Rn, so that tells us that Rn could be decomposed into S direct sum S perp. So we take that B, right? Take that B that we're trying to get close to. B then can be expressed as something in the first subspace and something in the second subspace, right? Something in S and something in S perp. So the first guy is in S, the second guy is in S perp. And it will turn out that claim this is P. This is the guy that we're looking for. So here's S, here's B. You can decompose B into somebody in S and somebody in S perp plus somebody in S perp, right? And this thing will be the P that you're looking for. Okay. Why? Why is that the guy that minimizes the difference? If we take any vector, say v and s, then, and let's look at the difference square. We're going to see that this thing is smallest. We'll see that this thing is smallest when v is bs, b sub s. Let's consider this thing. Right? We'll see that it's smallest when v is b sub s. So let's write this. And write this like this: b minus b sub s plus b sub s minus b. So we just throw in. We just be clever. We throw in a 0. Okay. Now notice, b minus bs is in S perp, right? Bs minus v is something in S minus something in S. So this is in S. Right? something in S perp and something in S. Yep.
Why is b sub s in S perp?
B sub s is not in S perp, but b minus b sub s
Oh, okay.
is in S perp, right? B is this minus b sub s is something in S perp.
Yeah.
Yeah,
that makes
okay,
sense.
good. Okay, so we have these two things and they're orthogonal to each other, right? There's something here and they're orthogonal to each other. And we're looking at the square of their we're looking at the square of this thing here. We're looking at the square of one vector and another vector. We're looking at the square of the magnitude of these two things which are perpendicular to each other, right? So you've got this, you got W1, you've got a W2, and they're perpendicular to each other, and you're trying to find the square of the magnitude. Well, by the Pythagorean theorem, you know that the square of the magnitude is going to be the sum of the squares of these two guys, because these are perpendicular to each other. Right? So by the Pythagorean theorem, this is going to be this squared plus this squared. Okay. Okay, and you see what that basically gives it to you. You see what happens, right? If v, right, as v ranges over all of S, what do we get? What's the smallest thing we could get? What's the smallest number we can get out of this? It's going to happen when v equals b sub s. When v equals b sub s, then this thing vanishes. When v is not equal to b sub s, then you get something bigger. You get something bigger than 0. Right? So what does it show us? That shows us that b minus v is minimized to smallest when v is b sub s, and only when. Like when and only when v equals b sub s. Right? Because when v equals b sub s, this term vanishes, and when v is not equal to b sub s, we get something larger. So what does that tell you? That gives us everything, right? That p is going to be this b sub s. and that happens only when B minus P is in S perfect. Yeah, that gives us the answer. Okay. Is that clear? Close your eyes for a second. Oh, raise a finger if you're confused. Okay, put down your fingers. Open your eyes. Okay. Okay, so you're, for the most part, people are okay. Let me see if I can say anything. Right. What we're trying to show right, we're trying to find, what are we trying to do? So keep, if you're confused, one good thing to do is to try to keep in mind what we're trying to do. We're trying to find the P so that B minus P, the norm of B minus P is smallest. Okay. So what do? We look at the norm. We look at the square of the norm, but that's okay. We're looking basically at the norm. We say, oh look, as V ranges over S, what do we see? That this thing equals this plus this, right? By the Pythagorean theorem. Okay. We use the direct sum decomposition, and we see this, that this thing equals this plus this. Right? We say, okay, well, for what V, we're trying to find the V for which this thing is smallest. So for what V is this thing the smallest? When V equals B sub S. Right? When V equals B sub S, because when that happens, this is 0. When that doesn't happen, this is some positive number. Right? So that basically gives it. It happens. This thing is minimized when V is B sub S, and it's only minimized when V equals B sub S. Okay, so that's the only thing. That's the only time it will occur. Yeah. So let me just tie it back, and then I'll let you go. So going back to our original problem, then, right? Right. We wanted x so that b minus a sub x was minimal. Now, what do we see? That's going to happen. That happens, we see now, as long as, or exactly when, b minus ax lies in the range of A perfect. Right? Because we need b minus the thing to be in the orthogonal complement of the subspace, right? So we need this thing to lie in range of A perfect. But that means that the thing must lie by the fundamental subspaces theorem. That means that we're looking for the guy who lies in the null space of AT. Right? That happens exactly when this thing lies in the null space of AT. So the problem becomes then this one. Solve AT b minus ax equals 0. Right? Solve for x. Right? Find x such that this equals 0. Right? In other words, such that ATB equals ATA A x hat. Let me write it the way it's in the book. ATA x equals ATB. Okay, so this is the problem that we need to solve. Using our knowledge of direct sums and orthogonal complements and fundamental subspaces, we find out that the problem of minimizing ax minus b turns into this problem, right? Solving this linear system. ATAX equals ATB. This is called the normal equation.